for that
Oh, you
cyber
would think
tech.
so. I'll tell you what. 2 years ago, I was sick of the Wi-Fi I was getting in my office. You might have heard this story, some of you. And because we're in that hallway, there's like one Wi-Fi hub. I'm forgetting the word right now. What's the word I'm looking for? Router, one router. And I was like, this sucks. So I brought in my own router, or I set up my own network. And that did not go over well. I was teaching a class one day. I teach for the Inside Out program. And that's like, most of my students are incarcerated. And I teach via Zoom. And one day I got this, they were working on something, and I saw this email from the head of IT security, and he's like, you need to call me Stat. And I was like, we've detected, like, you're in trouble, buddy. And I was like, oh, goddamn. So I called him, and he's like, yeah, we detected a rogue network operating in your office. And a rogue access point operating in your office. And I was like, yeah, that's me. You know? So I had to shut it down, and he's like, you do this again, you know, this is like I was already in trouble because I was teaching freshman seminar, and there was like some kind of group chat set up that I didn't realize, and I got this message came through on my text, and it said, Kayla has entered the chat. And I'd been spending the last year like trolling scammers. So like I'd get like people say like, hey, are you still coming? You know, you get those texts, it's like, where are you? You know, and they're supposed to bait you in. And so I said, oh, fucking Kayla. This was the person's name though.
It was me the whole time.
I was like, I am so done with her. And it turned out I was actually texting my entire freshman class who had not met me yet. And so I got a letter from the dean, an email from the dean with like a bunch of deans CC'd on it saying, we have an issue with you. And I was like, oh, my career just like flushed, all the blood left my face. I was like, this is how people go down. And once I explained, I think everything was okay. I'll tell you what, I was scrambling. Did that work out, Alexander?
Yeah, we got it.
Okay, cool, awesome. So I came back and I told my class, who were at various penitentiaries around about this, and they nicknamed me Rogue Access Point. And I was like, fuck yeah, I got a nickname already. The dude's in prison? That's like the coolest thing that's ever happened. So you probably don't have any questions yet. You might, I don't know. Is there anything from last time you want to like talk about? Okay. Did you get the email where I said that the web work, we're going to count the web work? So just so you know, that counts as part of like, you know, we're going to have those quizzes. And our first quiz, pre-class quiz is due next Wednesday before the start of class. That's open. I hope to God it's open. Does anybody know already? Let's try to check that before Friday, because I'll probably be out of the email from Saturday through Monday or something like that. So this will count as one of your your participation grades. So just do it. You need to do it anyway. Just do it. Yes, sir.
And what's that on? You said is it chapter 1?
Yeah, if you look, so actually do you have World Class there? Let's check it out. If you go to World Class, it should show up as a quiz. This is good, I'm glad we're talking about this. Yeah, yes.
I don't know why it's still 10:30.
Yeah, and it says,
It says Monday at 2 p.m.
I will fix that. It says it's due Monday at 2 p.m. That's a lie. I will change that to, Wednesday at 2 p.m. So it should be the 22nd. Could someone send me an email to remind me of that? Anybody?
I'll talk to you about it.
Thanks. Anybody? Yeah, 1 or 2, 10, just at least one. Greater than or equal to 1 email reminding me. Thank you. Okay, cool. So we talked last time about differentiation. We talked about this process, aka this. So when you see this, just think to yourself, what are you thinking about? What words come into your head? What comes into your head?
Derivatives.
What's that? Derivatives, yeah, cool. What's a derivative?
The slope of a function.
slope gives us the tangent slope, yeah? The one thing I want you to walk away from today with is that this is not a noun, this is a verb. Okay? We call it derivative, but it's a verb, it's a process. This represents the process of taking a limit of this difference, this average change, right? So the derivative is a process. The process we're going to talk about today is the reverse of that. And I'll make sense of what I mean by the reverse of that, because it is not even close to obvious why derivatives and the thing we're going to talk about today, definite integration, are reverses of each other. But let's get there. And let me tie this shoe so I don't bust my head open. All right, so we're going to start with a graph. We talked about that last time. Here's a function graph. That's every function graph I draw looks like that. That is the function graph that I draw. So, you've got some input x, you plug it into your formula, and you get out the y value here. Well, what I want to think about is this problem. What is the area under this curve and above the x-axis? So what is that area there? Now, the thing we're going to talk about can be interpreted as more than area, but I honestly believe seeing it as area is the best way to understand the process that we're about to talk about. So let's think about how we might do this naively. Now, what we're about to do, the Mesopotamians were doing this. The Mesopotamians, like a billion years ago, like it seems like a fantasy story, right? But the first civilizations were doing the thing we're about to do, and they were using it to compute the motion of Jupiter across the sky. If I said to you today, all you need for an A in this class is to compute the next position of Jupiter in the sky by the end of the semester without using any resources, go. How's that gonna work out? Not well, right? How about this? Make a spoon by the end of the semester. My God, could I in the rest of my life make a spoon? Given every bit I focus my life on that. The stuff people have done is incredible, is all I'm saying. We are standing on the shoulders of giants upon giants. These people they knew what was going on. So here we are today in a calc class doing what they did a long time ago. So I want to find that area. So a simple way might be to approximate this with a trapezoid. And maybe I connect these 2 points, and then I get the formula for the area of a trapezoid, which is, when we might know this from numerical methods even. What is it, numerical methods class? It's 1/2. It's the average of the heights times the base. Yeah, so we could use that formula. I think so. And we had numerical methods together too, didn't we?
I'm not in the class anymore.
You're not. You were. Oh, that's right. You were going to. That's right. You were going to.
Pull it out. Just have to have a schedule.
Yeah, that's right. That's right. Or I could break this thing into a couple of rectangles that approximate it, and get an approximation that way. Now that looks pretty terrible, right? The area of this rectangle plus the area of this rectangle. That's a shitty approximation of that area. It's kind of way under. How could I get it better? More rectangles, smaller bases. Yeah, absolutely. So, and saying that both ways is a super important way to think about it. So making more rectangles in our approximation is going to give us a better approximation. Conversely, or it's identically to say that we're going to make rectangles with smaller bases. Those say the same thing, and each one of them is going to give us a better approximation of this area. That looks pretty good. Yeah, not good enough to compute where Jupiter will be, but we're not going to have to do that. Luckily, I told you there's no projects, so you're safe from the Babylonian project. But let's come back to this. So in the 1800s, this process, early 1900s, this process was made rigorous by some people. You know, Newton knew about this. Newton kind of came up with this idea, but then a later mathematician, Riemann, really solidified this and gives us the process we talk about today as the definite integral, integration. And what the process is this. We're going to create a thing, just a quick overview. We're going to create a Riemann sum, which is an arbitrary bunch of rectangles, their area added up. And then we're going to let the number of rectangles go to infinity. And that's going to give us precise area. So I want you to see this because I want you to know this process, because guess what? You're going to see it again in multiple dimensions. Got a surface floating out here. Want to find the area under this table? Well, that one's pretty easy. But I want to find the area under this, the volume underneath this, between this and the floor. I'm going to do something very similar. So we want to first remember how to do this. Next week, we're actually going to be talking about surfaces and stuff. So super exciting. Let's say that's A, let's say that's B. And I have this closed interval A to B. So that notation, I just want to put it up there. Closed interval, and I have this function f of x that is continuous. What does that mean on that interval? Can anybody remember what continuity means? Come on, math people.
It has like no breaks in it.
No breaks, nice, very
Not
nice.
discrete.
It's lovely, not discrete, yeah, beautiful. Anybody got different verbiages?
I was gonna say for any input on the interval, there's an output from the function.
That can get us some nasty. Let me just give you one really quick. I won't even make it terrible. It's 1 if x is less than a half. It's 0 if x is greater than or equal to a half. So this function right here, Cormac, has an output for every input. But at 1/2, it jumps up to 1. And before 1/2, looks like that. So that's good. That's good. You're thinking about something a little bit different. So I can follow yours and still get a discontinuous thing. And I didn't do I had a crazy one I wanted to do. We're not going to do that yet. Kayla.
I don't know if this is 100% like correct thinking, but we can find like a derivative of every point, right?
That is a little stronger. So that's good. So continuity, let's just do a quick review of that. That's great. So the thing that I drew here is the derivative exists at every point. And to say a derivative exists means that there's a single tangent line that I can find. It's smooth. So a differentiable thing is smooth. But if I have this function, absolute value of x, looks like this. It is continuous. Yeah, it's continuous, but it's not differentiable here because there's an infinite number of tangent lines there. So continuous doesn't necessarily mean differentiable, but differentiable definitely gives us this. Does that make sense when I say it's stronger? Yeah, that's awesome though. Cool, this is fun. That's good shit. Anybody else got any other interpretations? Take real analysis. You'll soon be learning a much more rigorous definition of continuity with deltas and epsilons. But I won't make anyone do that because we don't need it for our business. So continuous, no breaks is a great way to think of it. There's no holes, there's no asymptotes, nothing like that. There's no steps, doesn't jump up like that function did. That was discontinuous at one point. So it's nice and continuous. And honestly, this could be made a little looser. This could have discontinuities in it, but we're not getting that fancy in here. And this process would still work. So what we're going to do is we're going to, maybe we can start over here. We're going to get a better pen. We're going to partition A to B, the closed interval A to B, into n subintervals. The way I'm gonna do this is I'm gonna pick some points in the middle. Let's think about this. If I wanted to cut this into 2 pieces, how many points in the middle do I need to pick? Just 1. If I want to cut it into 3 pieces, I need to pick 2 points. So I'm going to pick n-1 points inside here. So if that was, I wanted to put it into 7 subintervals, I'd pick 6 points inside here. And the way we're going to do this is we're going to pick some nodes inside there. So we're going to start with A is our first point. I'm going to call it x sub 0. So this is x naught or x0. Say naught if you want to sound like you know something, but it's x sub 0. And then I'm going to pick another one, x sub 1. It's going to be to the right of this one. I'm going to pick another one, x sub 2. Notice how I'm not making them even the same distance. Kind of spreading it out. It doesn't have to be the same distance, they can be all over. I'm gonna make x3 way out there, and then I'm gonna put a dot, 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 and then like right there is x sub n-1, and b is x sub n. Just so that we have a notation that is consistent with an arbitrary number. So if you notice here then, since I picked n-1 points inside, there are n subintervals inside there. So here's how we write this. We say A is the 0th point. We didn't even pick that, we were given that. X1 is bigger than that, X2 is bigger than that. And then all the way out here, I end up with the second to last. This one's the left, it's right in front of the right end point. And then X sub n is our B, like that. So that's a partition, I'm cutting it up. That's all that means. Is this all good so far? And stop me if it's not good at some point and ask. Or if you think of some weird complication or something, like say it. Awesome, so if you think something weird, we gotta hear it. So I'm gonna do that. And then the next step is inside each of these sub-intervals, I'm gonna pick any point I want to represent that whole sub-interval. So it could even be the left end point, it could be the right end point, but I'm gonna kind of make it look like it's in the middle. So this is my first representative. I call it x1 star. And then the next one's x2 star. So x1 star is in the first subinterval. It represents everyone in there. We're nominating a representative. These representatives can come from any point in the subinterval. So there's the first one, the second one, and then notice how the representative shares the same subscript with the right endpoint. So this one down here is x sub n star. You got x sub 1, 2, all the way up to n. There's n of them. I don't have n fingers. So in each subinterval, x sub I minus 1 comma x sub I. So this might be x0 to x1 or x1 to x2. That's what I'm trying to say there. Choose representative x sub I star. And this is for I runs from 1. And if you're a computer science person, you know, it's kind of like a for loop running through these indices here. Stop, tell me how that rolls. Do your best to really try to like take this in, because I'm not gonna quiz you on this. I'm not gonna give you any homework on it, but if you understand this, you understand calculus. This is what calculus is about, this process. We're gonna put some fancy symbols on the board in just a minute. This means this process. Okay, so now we're gonna pretend that there is a rectangle above each subinterval. To get the height of that rectangle, we're gonna take our representative and figure out what the height is there. So that line is f of x sub 1 star high. And I'm gonna make a rectangle across there that represents that whole region. So let's draw a little picture here. So this guy here is f of x sub 1 star high. The next one will be f of x sub 2 star, high. And so I got this guy here, so I go say, how high is the function right there? Okay, well you're the rectangle that represents the whole thing. Notice that the rectangle will change height depending on which representative I pick. So you slide those around, the rectangles are gonna be moving up and down. So 3 is, notice that f of x sub I star times xi minus x sub I minus 1. Now, this thing here, this is the base width. This is just the right endpoint on the x-axis minus the left endpoint. So, for example, what I mean here is f of x sub 1 star. That first rectangle times x2 minus x1. This is the height. This is the base. And if I multiply those two together, I get the area of that rectangle, the first rectangle here. And up here, this is equal to, let's do a little notation. This is f of x sub I star, the height, times the base width. We use delta to represent a change. So where delta, capital Greek delta, lowercase, looks like that. This is the change symbol in science and in math. And chemistry people probably, do I have chemistry people in here? Yeah. Chemistry, is like, you guys use this all the time, deltas, capital deltas. Right, isn't this the reason time flows forward? Change in entropy is always positive? Yeah, something like that. So, anyway. So delta x sub I is the width of the ith subrectangle. Okay. So far so good. How's the notation feeling? You're not going to have to get up and do this, right? I don't want you to have that kind of knowledge of it, but it's like, yes, I'm with you. Yes, I'm not completely blacking out. Kind of got it. Kind of got it. Don't know if I could repeat it, but I got it. Okay, any questions before I put this together? Because what I'm going to do next is add up all these areas and get my approximate area. So step 3, oh yes, was there a question or was that a sound or was that in my head? Okay, thank God, it was all of the above. Okay, that's fine. Agreed, it's at least in my head and also pen sucks. Pen still sucks. How's this greenie? Green's okay. Greenie's gonna do it for us. All right, so step 3 is add up, is that even visible? Step 4. Thank you. Step 4, thank you. Ooh, awake. It's good. Man, when people help me like get me back on track, it's like, thank you. You're here with me.
Gotta give you the eye first.
What's that?
The stare you
brow,
yeah.
Yeah, that's good. Yeah, do the brows, do anything. I'm checking brow like heights and how they're changing. I'm checking the derivative of your brow height. Well, this is derivative is 0. This is derivative is positive. I'm looking for 0 to see if there's a non-zero derivative on your brows. All right, so add up all the rectangle areas. And first I'm going to write this out without using summation notation. So it's the height of the first one times the width of the first one plus the height of the second one times the width of the second one. So this is this area, this is this area. Plus, wow, that looks so terrible. I hope you can see that. Dot, 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 plus, I'm not tall enough yet. F of x sub n star. This is the final one here. Whatever that height was. Boy, that's super shitty, but you get it. Delta x sub n. Add those all up. And that's the approximate area. The more larger n is, the better that approximation will be.
What does the delta mean?
change. That is the change. So delta down here, Atman, is it's the width of the base. Yeah, cool, awesome, good, thanks for asking. And so I'm gonna write this in a sum. So this is sigma summation. My index goes from 1 to n. The index is the part that's changing in the sum. Here I is 1, here I is 2, here I is n. And so I'm saying let this number run from 1 to n and add up all of these things. This is called a Riemann sum. Yeah? Yeah. That's cool, I'll take that. Derivative is infinite. Derivative is undefined when your head explodes. 1 over 0. All right, so questions. Notation makes sense. Anything I can clarify? Okay. So a Riemann sum. Now, this is approximate, so this is approximately the area. And if we were using a computer to do this, this would work great. And then we could let the computer do this to any arbitrary precision. Approximately the area. But what we're gonna do is let the number of rectangles go to infinity because we want ultimate precision. So as limit as n goes to infinity of this sum, so if you were doing this by hand, you would crank out this formula, God help you. And it would depend on n. What? And then you would have to take the limit. Now, right? It's whack. This process is written in this way. So when you see this anytime, and it's got numbers on it, it means what we just talked about. It is called the definite integral of f of x from a to b. Some of my friends in here will get to see this. Maybe real analysis, we'll see. The definite integral of f from a to b. Again, that's a verb, right? We call it the definite integral, but it means this crazy process that took, thousands of years of civilization to come up with. So, show it some respect. It's tough. And boy, does it sound hard. Thank God for the fundamental theorem of calculus. You might be thinking, that doesn't sound like something I should be thankful for at all. That sounds horrible. Well, the fundamental theorem of calculus makes this easy. So the fundamental theorem of calculus, FTC, fundamental theorem of calculus, could have probably written it out by that time. Part 1. Part 1. There's more parts obviously coming. Part 1 is the one we're going to use the most. And it says this, that this process is actually computable precisely by this difference. I gotta find this function big F and plug in B and take that same function big F and plug in little a and take the difference. And this where big F is any antiderivative of little f. Derivative of little f. I.e., if I took the derivative of big F, it's little f. Sometimes we call that the integral. Sometimes you say like, oh, I'll take the integral of x squared and it goes to 1/3 x cubed using the power rule. So that process that we say integration, when we do that, we mean that's the indefinite integral. So when we find, say, let's do this. There's no numbers here. There's no numbers at all. This is an indefinite integral. The indefinite, not definite at all, integral. So I'll do this one here. What, can anybody tell me what that is? Wow, we're,
1/5 x to the
I love it. Thought I heard 6 or something.
1/5.
Use the power rule. And then what would you tack on? Because you don't want to like hear about it.
Plus C.
Plus C.
Yeah.
Yeah, it's okay.
Sorry about that.
You have to hear about it. That's
Okay.
that's the penalty. So this process here is this thing. This is finding an antiderivative. This is the definite integral. So we sometimes say this is integration, but this is the process here. This is just the calculus part. This is the integral calculus. And the way, and finding these things is a big part of your suffering in like Calc 1, and then more importantly, Calc 2. This is where you suffer a lot. Trying to find those substitution parts. Oh man, it's a lot. That's what we'll review today in just a little bit. But so part 1 says this, where that is that. This is incredible, and I want to just point out something really incredible about this. That no matter what is going on, so here's A, here's B, there's some weird shit going on between here and here, we call it little f, but to actually find the area, I just need to know the value of a different function on the ends. Somehow everything is encoded about this middle part in this part of the process. So just think about that. And we won't get to this crazy part of Calc 3. We just don't have time. We need like another semester. I'm proposing Calc 4. We really need a Calc 4. Because one of the things you can understand later on is that if you've got some weird surface in space, you can do integrals of the whole surface by just knowing things about the edge of the space. And physicists do this stuff all the time. You've got like some kind of crazy object with static electricity going on it. There's all sorts of crazy shit flying through here, and there's particles fluxing out of here. Maybe it's an area of the ocean you're trying to understand. And you can understand everything inside by just understanding what happens on the edge. So this is a really profound, crazy part of calculus. But you're seeing it right here. You don't really think about how mystical this is in Calc 2, because you're struggling anyway. You're just like, shit, man, I just gotta get parts down. So that's part 1. Part 2 is actually the part that says integrals and derivatives are reverse of each other. And so part 2 says that if I integrate from a to a variable x of this function, and I use a different variable in here. So what this is this is saying that I've got this function from a to b, but I'm just gonna pick a point x and think about the area just between a and x. Then if I look at how fast that's changing with respect to the motion of this point, it's literally just the value of this function at x minus the value of that function at a. So think about this. If I didn't have this, you'd be like, oh, antiderivative time. I'm doing an antiderivative. But then when you take the derivative of the antiderivative, you get back the original thing. So here, the derivative is kind of on the outside. Here, the derivative is kind of on the inside because we're taking the antiderivative of that. So it's, anyway. We're done. Let's talk about how to find some rules. Let me stop for a second because that's a lot. Yes?
So the ddx can undo a different variable and it's
Yeah. Yeah, so let me give you a quick example. Absolutely. So if I said to you, I've got this function from 0 to x and it's sine of e to the 3t t squared dt, and that's pretty brutal. Like, we can't even do that. We'd have to get a computer. But if I said, what is the derivative of this with respect to, because think about this, this is actually a function of x right here. As this changes, you'll get different areas, right? So it depends on x. So if I think of it as a function with respect to x and take the derivative, the answer is that it's just this thing inside here evaluated at x minus this thing inside here evaluated at 0. And guess what? When I plug 0 in there, I just get 0, so it's just that. Does that make sense? Yeah. So that's what you're asking, kind of. Yeah, awesome. Any other questions? No? I guess just like with everything Regis, I have to bring my own freaking clock now. I have to bring my own pens. I got to bring my own clock because I have no idea what time it is. What time is it?
2:42.
2:42. We got a little time. What was that? I didn't hear it. Something happened. Something happened. I didn't get it. What's new? So let's review antiderivatives because you're certainly going to have to do them on that web work. And then Friday is come work, bring your laptops, we're gonna work on web work, okay? And there's stuff in there, if you know me, you know I put stuff in there I want you to ask about. That you're gonna be like, what? And I'm like, thank you, let's talk. Some of it's gonna be hard. So, that's good. I think the first half of that assignment roughly is derivatives, second half's integration. So let's just talk about rules here and just refresh our memory on those. And I'll just kind of whip out a few here so we just get it done. And I'm going to write these in U form in case we think about substitution a little bit later. But if I have the antiderivative of something raised to a power, I use the power rule. And with derivatives, it's like bring the exponent down and decrease this by 1. With integration, it's add 1 and divide by the new exponent. So take u, add 1 to the exponent, and then divide by the new exponent. Let's just pretend there's plus c's on all this stuff. Thanks. Got a limited pen ability here. Gotta conserve. So this is called the power rule, just like it is for derivatives. Power rule. And this is good as long as we're not dividing by 0. What n would make us divide by 0? -1. So this is good if n is not equal to -1. If n equals -1, we actually have this guy right here. 1 over u. Anybody remember what that is? Oh, yeah, beautiful. It's almost like you had Calc 2 just a few months ago. Yes, sir. Oh, should I put the plus c's in? This is like some teacher beat that into my skull a long time ago, and it's like, now it's just a comment for me. So we got that. So these are super important. Ooh, what's this baby? Oh, thank you. Yeah, isn't that great? Just beautiful. So sweet. And then I guess we've got some. Let me fill these out. Why don't you see what you remember? Oh, that was a jerk. I'm not going to do that. But I will put this and see if we actually remember, because I wouldn't expect you to remember that. But maybe you do. It's not pretty. It's not pretty at all. It says, can you see that, Alexander?
Did they talk about the tangent?
Yeah, yes. I would contrast that with, I would contrast that, I'll just put that one up there too, so we can get.
I know what you're talking about.
Yeah, you did, yeah, on a piece of paper,
Yeah,
right, somewhere.
1 over the,
Yep. would be like the old man at the bagging line. This is the poor dude who's like bagging your groceries because he needs the money because our economic system sucks. And he didn't keep his posture good. At least you could have your posture. Can't have Social Security. Everybody good. I'm curious. Yeah, this is like, you know this, or you don't, or you remember the trick.
I have a guess.
Yeah, what do you
Is
think
it
it
1
is?
over the square root of arc sine minus 1?
Wow, let me write that. I don't think so. 1 over what?
The square root of arc sine minus 1. I know that's the derivative or the integral of like one of the weird ones.
I don't think so,
No.
Brendan. No, but
Oh,
damn,
well.
man, A for effort. That's ugly enough. It's almost as ugly as the truth.
I know it's like 1 over the square root or something, right?
You're thinking of arc functions. You're thinking of like the derivative. I think what you're thinking about is this, like what's the derivative of arc sine of x?
maybe.
And that is this nuttiness, you know?
Yeah, something like that.
Yeah. Other guesses? What if I start?
Oh, yeah.
Yeah.
Nothing's clicking.
Yeah.
Anybody help me much?
It's cool. It's the natural log of secant of u plus tangent of u.
Yeah.
And yeah, of course, duh. That's a brutal one. The proof's cool. I'm not gonna get off on a tangent for it. It's really pretty. But you need to know a stupid trick. It's like trickery, just pure trickery. Talon, what'd you get for this one?
I got sine u.
I love that. Cool. Hey Zara, did you get this one?
Let me check my notes. I got negative cosine.
No, I love it. You said negative, I'm pretty sure. Yep, love it. Awesome. Takers?
Tangent.
Tangent, yeah! Because the derivative of tangent secant squared. There we go. Cool. Good stuff. So I think we have enough. Let's just get a couple formulas up here. And some of this is honestly going to have to unfold while you struggle. When you go to those problems I've given you, let's put up some special cases that you will definitely keep on a piece of paper. He's not here because I'm harassing him passive aggressively. Also possibly Alexander in this as well. But you're gonna have these on a piece of paper. And you're gonna use it while you're doing anything in this class that involves integration.
Yeah, okay. Yeah. I still have this piece of paper.
Yes, you do. Awesome. Fantastic. Hoffman, we were just talking about how good it is to write things on a piece of paper and have that piece of paper with you all the time. All the time. I missed you because I needed to harass you. So, and then sine of u, or sine of x dx is, what do you think that is?
K, X or KX?
Oh, sorry. Yes, thank you. Good call. Kx. Yes, sir.
1 over K cosine KX.
Yeah, with a negative. Yeah. Yep, cos kx. My God, my handwriting is devolving. Sorry. That's negative 1 over k cosine of kx. Yeah. And then, just see if you can do this one, just real quick. Don't say anything. Just do it. See if you can follow the. Here's the song. Here's how it goes. You got the beat. You got the notes.
This is 1K sine.
Sure is. Cool. Good stuff. Really good stuff to just have, because seriously, all the time, you'll have integral of cosine of 3x, e to the 7x. Just happens. So really quick then, integration by parts, the formula, because this will happen. We're gonna have integral of u dv. Now what this means is I have a product of some stuff in here, and I understand the parts of the product, but when they're put together, I don't have a nice formula for it. But if I had this alone or this alone, I could totally do the work. That's what this is for. So this is, were you gonna say something, Corbin? Sorry, you're just picking up the pencil. Okay, thumbs up, nice. So this is uv minus integral v du. This has the essential effect of flipping these two terms, so that instead of dealing with this and the derivative of this, you're dealing with the antiderivative of this and the derivative of this in your integral. And sometimes that can make life easy. I'll do a quick example so you see. But you remember this vaguely? It's actually the flip of the product rule. And that's how you would prove it. It's the flip side of the product rule from derivatives. So just a really quick example. If I said integral of x negative 5x dx, I'm gonna let u be the part that gets simpler when I differentiate it, and I'm gonna let dv be everything else. So I just put this little note here, the part that gets simpler. Now there's some cases, and when I say simpler, I'm gonna put that in quotes, because sometimes it doesn't feel like it, but I generally mean reducing the power through derivatives. It gets simpler when we differentiate. So which of these two things? I've got x times e to the negative 5x. Which one gets simpler when I take the derivative? X, right? Because it goes to 1. This stays the same complexity when I differentiate it. It's just like first derivatives, negative 5e to the negative 5x, right? The same thing, just got a different number out front. So, and then dv equals what's left, the rest of the stuff. And this, I don't know why I said, I should just be singular. And then what I do here is I differentiate to get du, and here I take antiderivative to get v. And then I just plug in the formula, and I hope to God that that integral I've got to deal with now is simpler. So let's do it here. We're gonna let u be x, we're gonna let dv be the rest. And we generally tack on the this is called the differential. It just to let you know what the variable is, because honestly, that's going to become a big play. We're going to have lots of variables in the future. So this keeps your eye on the ball. Can you just go ahead and do that for me, please? I got you set up here. Just try to refresh your memory, get your muscle memory and your brain. I guess there's brain memory. Everybody using this? Yay. Good. Usually carry the differential down, even though that's 1, I would write 1 dx. I wouldn't write the 1 even. Make sure you got, just a sanity check, make sure that's all going well. V is negative 1/5 e to the negative 5x. du is dx. Plug it into the formula. So I'm going to write this down again just to keep things sensible. So this is equal to u times v. So that's negative 1/5 x e to the negative 5x minus, the minus, it comes with the formula. If I get extra minuses, and it will, I gotta keep tabs on that. So integral v du, which just becomes dx. Sweet. So now what we've got is, I'm just gonna rewrite it. The minus minus becomes a plus. I'm gonna pull the 1/5 out in front. I guess I should have written this down. Just like the derivative is linear, the integral is linear. So the integral of a sum is the sum of the integrals, and constants can get moved out in front of the process. So like this. And so now I got a 1/5 here. They're gonna do that one more time, copy this. And then another negative 1/5 comes out in front to give me a negative 1/25. Fifth that's already there. E to the negative 5x. There's my plus c. How many folks got that? Okay, yeah, this is good. We got some practice to do. Definitely need some more. That's good. That's why we do it. What's that?
The negative 1/25.
So having that, so were you cool with up to here?
Yeah.
And then up to here?
Yeah.
So when I take the antiderivative of this e to the negative 5x using that rule, a negative 1/5 comes out in front of it.
Multiply them.
Yes, and I multiplied that by this. Sound good? Cool. Other questions? No. Does everyone have a way to do their web work? Anybody not have that? You can do it on your phone. It's not fun, but you can do it. Why don't we start on that? Does that sound okay? Yeah, let's just start on it. And how about start, let's see, let's find out what the first integral is. Let's try to get those knocked out, because we just did it. Might as well get some productive stuff done here, right? We really don't want work to do over the break, besides the prep work. Are you good?
Yeah.
Okay, cool. Okay. You can do it on your, I mean, so you can see because you'll have different versions, so you might want to just look at them. Theoretically, you have different versions. See, Carmick's doing it on his phone. Yeah, and he even said, Oh, wait, you do have a laptop.
I do, I just didn't want to pull it.
Oh my God.
It's a big one too.
It is, it's pretty nice. Is it a gaming laptop?
No,
No?
he's really bad at gaming.
Oh.
It's just CPU.
Oh.
Is that
That's it.
Yeah, that's it. Has everybody found the course? Yeah, that's it though, yes. I think I put and there is a link for it in World Class that, and you probably still have your stuff there. Yeah, cool. Yeah. Let me know if you're having trouble getting logged in.
Yeah.
That's one of the 13 problems. Who's peeking in here? They're not gonna expect this. Hi, just making sure everything's okay.
Yeah, no problem, it's gonna wait.
Awesome, we'll be done in about 15 minutes. Oh, that doesn't look good, Daniel.
Yeah, it's fine. It's old.
It's like blue screen of death.
Weird one.
I think Web won't build it.
Yeah, it's a highly evolved system that runs on like a 30-year-old PC in the ITS department.
I think it's a sign.
I hope not. Yeah, and feel free to like work together. We just want to figure this out. But make sure you understand. That's what matters.
Oh, it's from DevPros. It's like a weird.
Okay, cool. Okay, I thought it was like,
You can rewrite
what's it, a little farming?
Next to the one.
Not farming, not that, no, it's like,
Yeah,
Stardew. Yeah, I thought it was a Stardew thing, no.
Oh, yeah, no.
It's not, okay, yeah.
Yeah, yeah.
Is it the negative one or is it just 1/3?
Definitely negative 1/3 because it's in the bottom.
Yeah. And if you need anything, just ask me. Just get used to asking me for help when you need it. There's no sense in being too stuck. God. You want to sample this, Alexander?
Honestly?
Maybe.
Not.
Honestly, it
Wouldn't be
sounds-
the worst thing, I can make something out of it.
Sounds like it might, I could see you using this.
Alright. You asked.
What do you want, continuous, or do you want change?
I got it.
I do a consistent one. So I keep going.
Alright, I can do something.
There's actually a lot of depth in that sound.
I can definitely do
A
something.
lot of weird stuff going on. I look forward to.
I'll send you what I make with it.
Thank you.
If I make something with it. We'll see if I remember. You know, I
Yeah.
actually have a lot of voice memos where I'm like, oh my gosh, I could use something with this, and then never touch it.
Fair enough.
I feel like a slow build-up one might be cool.
I can make a riser out of it.
Yeah, I think that would be-
Yeah, that would be, like, we got like bend the pitch on it, like increase the sound even higher. Yeah, as a dubstep.
Dubstep.
Yeah.
Yes, sir. Yes.
Western.
It's good. Give me something to do. I'm bored.
Okay.
And I'm not really bored at all.
I don't know what's going on here.
Ooh, let's talk. Cool. Which one is that?
Or
Question
like I know what's
7,
going on.
No,
but,
no.
like, the answer that I answered
Oh.
is also the answer that it is, but it's incorrect. So I was wondering if there's like a formatting thing. that I'm
Oh, well, let's take a look. Oh, maybe. Oh, so you're positive in the answer. It's not the process that you're.
missing. Unless I'm
Query.
Is that saying like
Gosh, it
the
kind of
answer
sounds
is-
right. Can you show me your process?
Sure, so I just did, so with that, brought the two out front,
Yeah.
and then
Oh,
made it,
yep.
negative 1/3, and then differentiating that, and then, oh, I missed it.
There you go.
That's what it is.
That's very good. I thought there might be a process.
Yep.
Web work can be really bad on some things, but those kind of simpler ones, it's usually decent on.
Did you miss? I missed the two. I was supposed to, I didn't multiply the two back into it.
Order more new pens for this year. Oh, I can't.
What is proof?
Pens? Yeah, markers. It's got a shitty supply here. That is the end of the video. Got to get pens.